right, Mr. True. We're going to be taking a look at geometric sequences and series today. What is a sequence, since this is not day one?
A list of values is the set of positive integers.
Yep. List of values basically created by a function whose domain is a set of positive integers. What is an arithmetic? Actually, so I'll have to write the definition. What is the general term of an arithmetic sequence?
Is it a sub n equals a sub 1 plus b times n minus 1?
Excellent. By the way, tomorrow, Monday when you come in, I'm going to have a couple of nice challenge problems for you for arithmetic and geometric sequences.
Are we coming in tomorrow?
Yeah, you know what I mean? You know what it means when I say they're fun.
Are we coming in tomorrow?
Monday. My life stops without you. A sub n is equal to a sub 1 plus d times n minus 1. What is the partial sum formula for an arithmetic sequence?
2 times a1 plus an.
A sub n. Yep, so the sum of a n number of terms is n over 2 times a sub 1 plus a sub n. And now we're going to be moving into the geometric sequences. And for this time, I gave you a preview with the telescoping series example. Not that the book told you it was telescoping, and not that we had actually truly been introduced to series. But I gave you a little bit of a preview of the idea of series the other day with an expansion on one of the textbook problems where we were developing a partial sum of a difference of two fractions. So now we're going to really lean into this idea of the geometric sequence, and specifically a series. Okay, so a geometric sequence. A geometric sequence, what's the difference between a sequence which is geometric versus arithmetic, or just what's the general term of a geometric sequence? So a geometric sequence is you have a sequence of numbers where the ratio of each consecutive term is the same. So if we have a sub 1 and a sub 2 and a sub 3, a sub 4, and so on, up to a sub n, and arguably that could go on forever. If a sub 2 divided by a sub 1 is equal to, get your head on straight, equal to some ratio, and a sub 3 divided by a sub 2 is equal to that same ratio, and a sub 4 divided by a sub 3 is that same ratio, and so on, as you back divide a term with its previous term, a sub n divided by a sub n minus 1, if you get that same ratio over and over and over, then you are looking at a geometric sequence. So it is a sequence of numbers that are not created with some kind of repeated addition of a common difference, but is a sequence of numbers that is created by a common ratio, a common repetitive multiple of the same number. So the general term of this arithmetic sequence is going to be equal to, sorry I didn't have that down yet, is going to be equal to a sub n is equal to a sub 1 times r to the n minus 1. So we still have that n minus 1 expression in both the arithmetic and geometric sequences, because we add n minus 1 number of times a common difference to the first term to get our general term in an arithmetic sequence, and we multiply by r and n minus 1 times to the initial term to find a general term of a geometric sequence. Well, there's a special formula for finding a partial sum if you have a geometric sequence, just like if we have an arithmetic sequence, but it's not the same formula. So your S sub n, your partial sum, is equal to a sub 1 times 1 minus r to the n, divided by 1 minus r. Not quite as easy to sort of derive that formula as it was for the partial sum of arithmetic, so I'm just going to give you that without sort of like a derivation or example of where it's coming from. Just that is the partial sum formula. Yes, ma'am?
Does the A always like remain off in the numerator and not on the
I wrote it a
side?
little bit different in the book. It's the same thing though. Because when it's out front, you can do that a sub 1 over 1, and that'll distribute it to the numerator.
Okay.
Now, the difference here is, with a geometric sequence, the door is open to the idea of a series, where we add an infinite number of terms, not adding a set number of terms. So there's going to be a formula here where we have S is equal to a sub 1 over 1 minus r. And it would not make sense for r to be equal to 1, that our common ratio be 1, because when you multiply by 1, you're not going to have any growth or decay in those numbers. You're just going to have like 5 times 1 is 5, times 1 is 5, times 1 is 5, times 1 is 5. If your r value is equal to 1, you really don't have a geometric sequence, you have an arithmetic sequence, where the common difference is 0. So, not only can r not be equal to 1 because you can't divide by 0, but it wouldn't make any sense with a geometric sequence for r to be equal to 1 because you will not create a geometric sequence. You'll create an arithmetic sequence with a common difference of 0. So, this formula of s is equal to a sub 1 over 1 minus r, that will always give you a number, but it will not always give you a valid number. So, a series, there's no subscript of n. A series is you are adding an infinite number of values. So, if I say a sub 1 is equal to 1, and our common ratio is 2, giving us a general term of a sub n is equal to 1 times 2 to the n minus 1, then as I create that list of numbers, a sub 1 would be 1, multiplying by 2 to get the next consecutive term, the next number would be 2, multiplying by 2 to get the next consecutive term, almost like working with a recursive type setting because I'm doing this in my head, the next term is going to be 4, then 8, then 16, and then so on and so on. Think about adding those numbers. If you added an indefinite number of these terms, now if I say 1 plus 2 plus 4 plus 6, if I say 1 plus 2 plus 4 plus 8 plus 16, that right now is what? The sum of 5 terms. And I don't really need to use a partial sum formula to add those up because I can do it so easily in my head. It might be fun to use the formula and then compare the answer the formula gives me, the partial sum formula gives me from what I can do in my head, but that's a partial sum. If I come through here and I do a little plus dot dot dot, that indicates that I'm not adding 5 terms. That indicates with the plus 3 dots that I'm just adding forever. And does this series exist? Does this sum exist? Well, if I don't put my thinking brain on and just go, oh, Mr. True gave me a formula for the sum of a series, the sum of a geometric series, then I'm going to get S is equal to, what's my first term in that sequence? 1. Well, sequence if it's a list, a series if it's an infinite sum. Over, so a sub 1 over 1 minus r. What am I multiplying by? What's the common ratio? 2. So that means that the sum, when I add 1, 2, 4, 8, 16, and I never stop adding, this formula of S equals a sub 1 over 1 minus r is going to give me 1 over negative 1, which is negative 1. Does that make any sense at all? We're adding a bunch of positive numbers. Of course, we're never going to get a sum that's negative, and we certainly will not get a sum of just simply negative 1. You know, what does this add to? I mean, I know 1 plus 2 is 3, obviously, plus 4 is 7. But if I add this forever, what's the sum going to? yeah, these numbers keep getting bigger and bigger. The sum is infinity. That does not exist. That's not a real number. It's an idea or a concept. But in calculus, we say that this series converges. And by the way, the series would technically be the summation, where I starts, or n, starts at 1 and goes to infinity of basically, I'll write 1 just for notes, 1 times 2 times I to the negative 1. We would say in calculus that that series diverges, that that series does not exist, that that series does not approach a real limit, a real value. So, I'm throwing some calculus language at you because, well, this is called what? Pre-calculus. But for a lot of this, it might be just sufficient to say the series is a sub 1 over 1 minus r when the absolute value of r is less than 1. When the r value is greater than 1, you might still be asked to find an infinite sum, but it's up to you to realize that it doesn't exist. It's up to you to, every time you're asked to find a series value for a geometric series, that you must check the condition, that you have to make sure that the absolute value of r is less than 1. And if you don't, and you just do rote memorization of a formula, you could very well get an answer that doesn't make any sense. But you will get an answer, and I get a lot of kids that, give me pretty ridiculous answers, because, well, the formula said it was negative 1, but it's not. So there is a condition with the idea of the infinite sum, the series value of a geometric sequence. Cool? So, make sure you think about that full idea. Simple formula, and but super powerful. This formula and this idea of an infinite geometric series existing is an incredibly large part of the foundation of basically the last chapter of Calc 2. I mean, the use that it comes back and how it's used at a very high level of calculus is really quite astonishing. Basically, let's do another example. So let's say we have a sequence of 16, 8, 4, 2, 1, 1/2. First of all, let's start with part A. What type of series is this? Not worded very well, but identify the type of series given. Basically, all you have to know is arithmetic, geometric, or neither. Okay, we're only studying 2 types of specific sequences. 8 minus 16. We have a common difference of negative 8. 4 minus 8. We have a difference, I should have said common. We have a difference of negative 4. 2 minus 4. Difference of negative 2. And, yeah, that's not a common difference, so it's not arithmetic. Now, we talked about maybe second and third differences, giving general terms that are maybe quadratic or cubic, but in terms of name, arithmetic, geometric. And these are not common differences, so this is not arithmetic. So let's back divide. 8 divided by 16. That's an r of 1/2. 4 divided by 8. That's an r value of 1/2. 2 divided by 4. An r value of 1/2. So it does appear that we have a common ratio of 1/2. So yes, this is geometric, with an r being equal to 1/2, and the absolute value of r is less than 1, which opens the door, so therefore S exists. This geometric series, or this geometric sequence, can exist as a series. There is an infinite sum when you add all of these numbers forever. These numbers, when you add these forever, will never be exactly some value, but they will approach. Like an asymptote, when we graphed rational functions way back in like chapters 1 and 2. When we found equations of those horizontal asymptotes, we were finding limits as x approaches infinity, or arguably negative infinity as well. So it does tie back into that, which I don't want to do a full-blown discussion about that. But this also is not enough of a condition. Otherwise, the end of Calc 2 would be so much easier. But these numbers you're adding by are getting smaller and smaller and smaller. The numbers you're adding by are approaching a value of 0. Now that arguably is not enough for a series to exist, but we're not going into like Calc 2. So in terms of a geometric series, we can recognize that these numbers are getting smaller that we're adding by because we're multiplying by 1/2 to get the next number. And these values of 8, 4, 2, 1, 1/2, the next one of course will be 1/4 and then 1/8. These values are going to approach 0 fast enough that the infinite sum will stop growing because we effectively start adding by 0. But you have to approach 0 fast enough. So our infinite sum, since we know it now exists, for part B, our infinite sum is going to be a sub 1, which is 16, divided by 1 minus our common ratio of 1/2, which I've already put some thought into and recognized that the absolute value of r is less than 1. And we get 16 over, what's 2 minus, 2 over 2 minus 1 over 2? Of course, that's 1/2, which means we have 16 divided by 1/2, which is the same as 16 times 2, or 32. So we can start by adding, we can start with 16 and add by numbers that have that become smaller by a factor of 1 over 2. 16 plus 8 plus 4 plus 2 plus 1 plus 1/2. You can add for the rest of your life, but you'll never get a sum that is bigger than 32. It will never be over 32. But it'll approach but never become 32.
What did you say equals 32?
It's I'm going to say S is equal to 32, but the infinite sum is truly approaching 32. Okay, it's never really actually equal to. Okay, we good with the idea of geometric sequences? And actually, we've already done an example of an infinite sum. Should we do partial sum?
Yeah.
Yeah.
Let's do something super easy. Okay, let's just add the first 5 since it was up there. It's not super interesting, but the sum of the first 5, S sub 5 is 16 plus 8 plus 4 plus 2 plus 1. And arguably, why would I go through a fancy formula that's hard to remember when there's only 5 numbers? I wouldn't. 16 and 4 is 20. 8 and 2 is 10. So now we're up to 30. The answer is 31. But let's play around with this new formula. And, maybe we're adding 60 numbers. Right? I don't want to write out 60 numbers and add them all. So let's see how this formula works. S of 5 is equal to a sub 1. Our first term was 16. We already maybe had this question that asked, identify the type of sequence. We looked at common differences, common ratios. We determined it was geometric. We know r is 1/2. So we got 1 minus 16 times 1 minus 1/2 to the 5th power over. I can already see why the heck would I do. I don't want to do 1/2 to the 5th and all this fraction work. If I don't have to, over 1 minus r. So 1 minus 1/2. So this is going to be 16 times 1 minus, what's 2 to the 5th? 2, 4, 8, 16, 32. So we have 1 over 2 to the 5th is 1 over 32 over 1 minus 1/2, of course, is still going to be 1/2. Okay. Well, 16 divided by 1/2 is 32. So we're going to flip this 1/2 up and get 32 times, this is 1, So if we find that common denominator, 1 with a common denominator of 32 is 32 over 32. So 32 minus 1 over that common denominator of 32. Okay, this wasn't quite as bad as I thought. The 32's cancel out, and we get 32 minus 1, which is once again, whew, didn't make a mistake, 31. So we got the same answer. So at least you can see that this formula works. Of course, if you're given a formula in the textbook, you know it works. But we practice working with it. And we got the same answer as we did just simply adding those 5 numbers. The point of this is not to add 5 numbers, right? You're programming, you're doing Excel spreadsheets, you're doing some kind of higher level math, you've got like massive amounts of data. That's where these formulas come into play. Excuse me, for this example, which we're going to take a look at, it's not 33 in your book anyway. We're going to have the summation, or sigma, the summation of 5 times 2i, which I'm like parentheses. 5 times 2i, where I starts at 1 and goes to 10. And we want to evaluate this partial sum or infinite sum? This partial sum or this series? Is this a series or is this a partial sum? Partial sum. Why is that, Ian? Yeah, we start at 1 and goes to 10, so we're going to add 10 numbers. Excellent. Okay, it's only 10. We could arguably break the 10 out. But also, we learned how to work with sigma notation with both arithmetic and geometric. Or maybe this is neither. So, I don't want to just plug and play with my calculator, even though maybe in the real world that's a lot of people are doing. But if we actually want to understand what's going on, we may actually want to or need to write out a few numbers to make sure we understand what type of sequence is going to come out of this general term. We do have a base with an exponent, and exponents do indicate repeated multiplication. So I'm thinking this is probably going to be geometric. Okay, I've got a base with a variable exponent. It really kind of is strictly geometric. But if you're unsure, do an expansion and make sure that you know whether this sigma notation is giving you an arithmetic sequence for which we can use this formula, or a geometric sequence for which we have a new formula. So I is equal to 1. We have 5 times 2 to the first power. And the sigma, given you repeated addition, we're going to let I equal 2 and have 5 times 2 to the second power. And maybe just one more. Plus 5 times 3 to the third power. 2. Thank you. To the third power. And of course, I don't want to write out 10 of these. So 5 times 2 is 10. 2 squared is 4 times 5 is 20. Plus 5 times 2 cubed, 2 cubed is 8. Times 5 is 40. Okay, we can see that common ratio of what? What's 20 divided by 10 and 40 divided by 20? 2. And what is our first term?
5.
Not 5. It looks like it's 5 in the a sub n expression, but that's another reason why you want to start an expansion of sigma, so you make sure you say the right answer, and you most often are helping me, not vice versa. But a sub 1 is equal to 10, r is equal to 2, and so s sub 10, don't be too quick to look at the top and say it's 10. What if my lower limit was 2? It would be s of 9, not s of 10. Okay, so letter is terrible. We do have a lower index of 1, and so, yeah, s of 10 is a sub 1 times 1 minus r, which is 2, to the, n power. I'm pausing because it also might be a good idea, especially if this lower index is not 1, that can really throw things off. This is a sub 1, this is a sub 2, this is a sub 3. Not because, this isn't a sub 1 because the lower index is 1. This is a sub 1 because it's the first number that came out of the sigma notation. I mean, these could get tricky. Of course, my lower index is 1. And I did plug in 1 to get the first number. But the domain of sequences is positive integers starting at 1. That's not necessarily how sigma notation works. So, n is 10, right? 10 times 1 minus 2 to the 10th, that's going to be a big number, over 1 minus a common ratio of 2. Of course, 1 minus 2 is negative 1. So, we have negative 10 divided by negative 1 is negative 10 times 1 minus 2 to the 10th. And yeah, I have no idea what that is, so I'm just going to leave my answer like that.
1,024.
You guys are so annoying. Okay,
What was it?
I don't know, but they're going to make me write it out.
No, it's 1,024, I was right.
Negative 10, parentheses,
No, well, that's what
1 minus 2, shut up, to the 10th power. I hope you're both wrong. 10,230.
Good job, Sam.
I'm right.
Okay, next example. What else do I like in here? So let's take a look at this example. Hopefully after this one we can get a good idea of how to do this. I'm going to give you a minute to try this. We have the summation where n starts at 0, okay, a little bit different, and goes to 20 of 3 times 3 halves to the n power. Okay, now I'm going to show you a little, I don't know if I'd call it a trick, but I'm going to show you an adjustment that I would have never thought of if I wasn't currently a calculus teacher. There is no reason why we couldn't just keep this in this format, except maybe for the correct use of your partial sum formula and being able to more easily understand or identify what n is. What's the domain of sequences? Positive integers starting at 1. That's not the same with sigma notation. I could literally make this lower number negative 7 if I wanted to, and that would really make this problem tricky. And when you're at the end of Calc 2 and you're doing like super hard, ridiculous problems, I mean, I really struggled, internalizing that chapter for myself. Some of you probably would get it faster than me, but that's me. I found it necessary to make my notations because it was so complex to perfectly, exactly match the formulas in the book. So let's let the lower limit be 1. So the lower and upper index of the sigma notation exactly matches at least what we know right now, which is the domain of the sequence. Let's make this start at 1. Okay, so I'm going to add 1 to the lower limit, thus I'm going to add 1 to the upper limit, so I have the same number of terms. So I'm going to make an adjustment here to this question and make n start at 1 and go to 21. My first number that I was supposed to plug in was 0. Now the first number I plug in is going to be 1. But I can't change the value of each term in the sequence, each term in the expansion. So when I plug in 1, I need this exponent to be 0 like it would have been in the first place. I added 1 to the lower and upper limit or index of the sigma notation. So if I added 1 to these values I'm plugging in, I have to do what to the exponent or what to wherever the n is to cancel out that addition of 1. I just added 1, I need to cancel that. Subtract 1. So I added 1 to the lower and upper indexes or limits. Thus, everywhere there's an n, I need to subtract 1 in the a sub n expression, and then it's going to be okay, it'll still work out. And then my lower index, my lower limit of summation notation, or sigma, will match the domain of sequences, and it makes the question easier. So, still with the suggestion that you should expand a little bit, even though I see a constant base variable exponent, it's going to be geometric. But let's do the expansion. Let's plug in 1. So we have 3 times 3 halves to this, well, 1 minus 1 is 0 power. So that's 3. And then that's basically a sub 1. Now a sub 2 is going to be 3 times 3 over 2 to the 2 minus 1. Well, 2 minus 1 is 1. 3 halves to the 1 is 3 halves times 3, which is 9 halves. Now, we have a constant base variable exponent with just a sort of initial value out front, so we're perfectly matching that pattern of a geometric series. So I don't need to do this expansion anymore and work a lot of fractions. I just wanted the first term. Why are you letting them out? Oh, you're not. Who's? Oh, you're leaving. Okay. Peace out, dog. All right. So our partial sum, S sub 1 to 21. How many terms do we have? 21. S of 21 is going to be a sub 1, or 3, times 1 minus, what's our common ratio? 3 halves to the n power, the 21th power. No, we're not going to actually do that. We're going to just write it out. Over 1 minus r, or 1 minus 3 halves. 29,921. Thank you. All right, that's the end of our last example. See you on Monday. Woo! Bye.